In the previous video, we saw how to put generic specialization to work to improve the performance of our generic code. In this video, we'll begin our discussion on algorithms by comparing a linear search against a binary search. To be clear, the goal of this discussion is not to give you a specific tool that will solve all of your performance needs, but help to build awareness of the performance implications behind your programming choices. We can think of an algorithm as a step-by-step strategy for solving a problem. Of course, there are many ways to solve pretty much every programming problem you come across in Swift. So the question becomes, how do we determine which strategy or algorithm is the right one for the job? Big O notation is a way to classify and communicate the efficiency of software algorithms as their input size n grows. The best way to understand Big O notation is by comparing and measuring algorithms. Let's create a new Xcode project with unit tests. Once your application is loaded, add a new file named Big O and provide a class with the same name. We'll add 3 properties. We'll name the first property Giant Number and give it a value of an array of ints and initialize it to hold 100 million integers. The other 2 properties will serve as counters to track how many steps each algorithm takes. We'll name one linear steps and the other binary steps. We're going to use 2 different approaches to finding our specific number in our array. Our first approach is a linear search, which uses brute force to iterate through the array sequentially and find our value. The next approach is by using a classic binary search. A binary search allows us to apply our knowledge about the data to help reduce the criteria of our search. Since we know the lowest number we have is 1 and the highest number is 100 million, we can eliminate possibilities in an elegant manner. We'll define a function named linear, which takes an int, and then we'll add a simple for-in loop that contains a check for our value. When our linear search succeeds, we break out of our loop. Our linear function can be described as an O times n algorithm, meaning that the order of complexity increases evenly by the number of items that we're iterating over. Next, we'll define a binary search function, which is an O times logarithmic n algorithm. This means that while the input number increases, over time the complexity increases, although much less significantly. I'll go ahead and paste in the code and explain it line by line. This function takes 3 ints as arguments: a value, a start index, and an end index. Then we locate the middle index and use that index as a key into our giant number array. Then we check to see if our selected number is greater or less than the value given. If it's greater, we'll reduce our range. If it's less, then we'll increase our range. If it's not one or the other, then we have found our number. Then we'll create wrapper functions to call our algorithms from our tests. And then we'll set up our tests. At the top of the test class, we'll create an instance of our Big O class. Then we'll add 2 test functions, one for our linear test and one for our binary test. Once they're wired up, we'll run our tests to see how they perform. In my test, the linear search takes about 9 seconds to perform, while our binary search takes only a few thousandths of a second. The reason why the binary search is so much faster is that it took only about 260 steps to complete, while the brute force linear approach had to step through each item to find our value. Our test perfectly illustrates the power of selecting the right algorithm for the job. Of course, the complexity of the implementation needs to be balanced with the magnitude of the task at hand. In other words, we don't need to implement a binary search algorithm to search through a 10-item list. But regardless of the task at hand, we should always bear in mind the complexity of the algorithms we choose. To see more comparisons and to find a link to an excellent repository containing popular algorithms written in Swift, visit this video's resource page. In this video, we looked at 2 different algorithms for a common problem. In the next video, we'll learn about an algorithm that caches computations.